Hey everyone. Back in school, we were all taught a simple rule. A meter is just a standard unit of length. It is the distance between two marks on a ruler. Nobody explained why it was exactly that long. We just memorized it and moved on. Today, there is a modern definition you can look up anywhere. A meter is the distance light travels in a vacuum in exactly 1/299,790. 2,458 of a second. That sounds precise. It sounds official. But sit with it for a second, and a strange question shows up. What is the speed of light, exactly? It is 299,792,458 meters per second. Do you see the problem? To know how long a meter is, we need to know the speed of light. But to measure the speed of light, we need to already know how long a meter is. That is not a small technicality. That is a closed loop. You cannot climb out of a circle by walking further around it. If you ever noticed this loop and felt confused, you were right to feel that way. This is not a silly question. It is a real logical puzzle, and it took physics centuries to actually solve it. So how do scientists get away with defining a unit using a number that is itself measured in that same unit? The answer is not a trick. But to see it clearly, we cannot start with lasers and atomic clocks. We have to go back to a much cruder tool, a metal bar locked away in a vault in Paris. At the end of the 1700s, France was in the middle of a revolution, and not just a political one. Before this, every region had its own version of a foot or a pace. A merchant in one town could get cheated just by crossing into the next town, because the units simply did not match. French scientists want something better. A unit of length based on nature itself, not on any king's foot. So they picked the Earth. They decided that 1 meter would equal 1/10,000,000 of the distance from the equator to the North Pole, measured along the meridian that runs through Paris. That is a clean idea on paper. In practice, someone had to go out and actually measure a chunk of that curve. Two astronomers, Jean-Baptiste Delambre and Pierre Méchain, took on the job. Starting in 1792, they spent years dragging surveying instruments across France and Spain, measuring the arc of the meridian from Dunkirk down to Barcelona. Méchain was a perfectionist. When he reached Barcelona, his measurements of latitude did not line up the way they should have. The cause was subtle. Something about how light bends slightly as it passes through the atmosphere, a detail nobody fully understood yet. The mismatch haunted him. He hid the discrepancy, and he kept trying to fix it in secret. He went back to Spain years later to remeasure everything, and he died there of yellow fever in 1804, still chasing that error. Historians still debate exactly how much his mistake really changed, but the story of his obsession is well documented. Because of that small error, the platinum bar cast in 1799 to represent the meter, known as the Mate des Archives, ended up about 0.2 millimeters shorter than the original goal. That is roughly the thickness of 2 pages in a book, tiny. But it was now permanent, locked into metal. In 1889, the world upgraded to a sturdier bar made of platinum and iridium, kept in a vault at Sèvres, just outside Paris. But here is the deeper problem. Any physical object has weaknesses. It can wear down. It can expand in the heat. It can gather dust. It can be lost in a fire or a war. If that one bar in that one vault shrank by a single micrometer, would the entire universe have to shrink with it? Of course not. But officially, for every ruler on Earth, it would. Science could not build its foundation on an object that quietly changes size depending on the room it sits in. What we needed was a ruler that could never drift. Light seemed like the obvious answer, but switching to light triggered a brand new crisis in the lab. To get away from the metal bar, scientists first tried something a little stranger. In 1960, the meter was redefined using light from a krypton 86 atom. 1 meter became exactly 1,650,763.73 wavelengths of a particular orange-red light that krypton gives off. That number looks intimidatingly precise, and for a while it was the best tool available. Then, in 1972, a physicist named Ken Evenson led a team at the National Bureau of Standards in Boulder, Colorado. Their goal was to measure the speed of light more accurately than anyone ever had, using a laser stabilized by methane gas. Here is the physics they leaned on, and it is simpler than it sounds. For any wave, speed equals wavelength times frequency. Picture a wave in water. If each ripple is 1 meter apart, and one ripple passes you every second, the wave is moving at 1 meter per second. Multiply how long each wave is by how many pass per second, and you get the speed. Evenson's team measured their laser's frequency at 88.376181627 terahertz. That is over 88 trillion cycles every second. They measured its wavelength at 3.3922231376 micrometers, an almost impossibly small distance. Multiply those two numbers together, wavelength times frequency, and you get the speed of that light. Their result was 299,790,2456.2 meters per second. That was 100 times more precise than anything measured before. Here is the part that should surprise you. Evenson's team wanted to push the precision even further, and they hit a wall. Not because their laser was flawed, because the ruler they were measuring against was flawed. The krypton 86 light used to define the meter was not a perfectly clean signal. Its spectral line was slightly smeared, slightly asymmetric, blurred at the atomic level by the physics of a hot gas. So think about what that means. Physics was not stuck because the instruments were bad. Physics was stuck because the very definition of distance was too fuzzy to measure against. The ruler itself had a margin of error built into its atoms. If the ruler is the thing holding you back, why not throw the ruler away and use the speed of light itself as the standard? But that idea runs straight into the same trap from the beginning of this video. How do you build a unit of length out of light without falling into that same endless loop? In 1983, the General Conference on Weights and Measures made a decision that sounds almost too simple to be revolutionary. They stopped trying to measure the speed of light. Instead, they froze it. From that point on, the speed of light in a vacuum was declared an exact number with zero uncertainty, not approximately 299,792,458 meters per second. Exactly that. Here is how that move breaks the circular trap, one step at a time. Step 1. Light moves through a vacuum at a constant speed. That is a property of the universe itself. It has nothing to do with which ruler a human being happens to be holding. Step 2. We can measure time with incredible precision using atomic clocks built from cesium atoms. These clocks are accurate to about 1 part in 100 trillion. They would not lose a full second in several million years. Step 3. And this is the part that unlocks everything. Imagine firing a beam of light out into space and just watching it travel for exactly 1 second. In that 1 second, the light covers a real, physical, fixed distance. That distance is completely determined by nature. Let us just call it 1 light second. Step 4. A light second is a huge distance, far too big for everyday use. So we take that distance and slice it into exactly 299,792,458 equal pieces. Step 5. One of those tiny slices is what we call 1 meter. Say it slowly and the trick becomes obvious. We are not using meters to define the speed of light anymore. We are using time, 1 second, and a physical phenomenon, light traveling through empty space, to build a fixed distance. Then we cut that distance into equal parts. This is an intuitive way to picture it. In real laboratories, physicists actually use lasers and interferometers to count light waves directly, but the core logic never changes. We are slicing space using time. You might be wondering something else. Why 299,790,2,458? Why not just round it to an easy number like 300 million? Here is the reason. If they had picked 300 million, the new meter would have come out slightly shorter than the old one, by a couple of millimeters. Every ruler on the planet would have instantly become wrong. Every blueprint, every steel beam, every road sign built to the old meter would suddenly be off. So they chose the one number, down to the last digit, that made the new definition of a meter land exactly on top of the old one, the one measured by that platinum bar and by krypton light for 2 centuries before it. That single decision did more than fix a laboratory bottleneck. It quietly rewrote what a meter actually is. Here is the idea that changes how you should picture the ruler in your hand. Length is not really its own separate thing floating out there in the universe. Length is something we build out of time. When you hold a meter stick, you are not really holding a piece of space. You are holding a frozen measurement of time. That stick is quietly telling you, this is exactly how far light travels in 3 nanoseconds. You can see this same idea at a much bigger scale. When scientists want to know the distance from the Earth to the Moon, they do not stretch out a tape measure. They fire a laser at a small mirror that Apollo astronauts left on the lunar surface decades ago, and they time how long it takes the light to bounce back. That round trip takes about 2.56 seconds. Divide that in half, and light took about 1.28 seconds to travel one way. That works out to about 384,000 kilometers, not measured in space, measured in time, and then converted into distance. This is also exactly the direction Albert Einstein was pointing toward with relativity. Space and time are not two separate independent things. They form one connected structure, space-time. The speed of light is not just how fast one particular thing moves. It works more like an exchange rate, a fixed number that converts a stretch of time into a stretch of space, and back again. From the astronomers dragging survey chains across muddy fields in the 1790s, to physicists locking a laser onto a single methane molecule in a lab in Colorado, humanity spent 2 centuries building toward one quiet realization. Distance was time in disguise the entire time. So let's bring this all the way back. A meter is not a metal bar hidden in a dark vault in Paris. It is not an arbitrary line someone drew a long time ago either. A meter is what you get when you combine one unchanging fact about the universe, the speed of light, with the most precise tool humans have ever built, a clock. Math and physics are not just a pile of arbitrary rules you were forced to memorize in school. They form one tightly connected system, a quiet agreement that lets a scientist in Tokyo, an engineer in New York, and you, holding an ordinary ruler, all speak the exact same language about reality. If you have made it this far, subscribe to Axiom Code for more of these hidden stories buried inside the numbers we use every day. And if you want us to dig into the mystery behind another unit, maybe the second, or the kilogram, or anything else in math that never quite got explained to you, leave it in the comments. It might be exactly what we decode next.